In order to illustrate how Lenz's law plays hand in hand with Faraday's law, I want to introduce you to a popular demonstration. It's one of the classic examples of Lenz's law in which you drop a magnet through an aluminum tube. So I don't have an aluminum tube, but I do have a picture of an aluminum ring. Now I choose aluminum as the material because, as you're probably aware, the magnetization of aluminum is very low. It's a metal that doesn't really interact with a magnet. So you wouldn't expect that the magnet would stick to the aluminum or vice versa. But there is a force that appears when the magnet interacts with the aluminum in this way. If the magnet were to be dropped from rest and approaches the tube and then falls through it and comes out the other side, there'd be a continuously changing flux as that process takes place. So let's look at the initial condition. Right now, there's a little bit of magnetic field passing through the aluminum ring, right? There's this field line that passes through. Now, that field line and that field line don't quite make it through, and so don't contribute to the flux. So there's some initial amount of magnetic flux here. Okay, well, as the magnet drops a little lower, now at this point, there's a larger amount of magnetic flux. All the field lines now pass through the ring, so the flux is increased. So the response to an increasing flux is a current. An induced voltage drives a current around the ring. So the question is, which way does that current flow? If you understand Lenz's law, it's easy to answer that question. So let's see. The current's either going to flow this way, counterclockwise, or the current's going to flow the other direction, clockwise. So which one is it? Well, it's going to flow in such a direction that it opposes the very change in flux that induced the current in the first place. That's a mouthful, isn't it? Let me try to illustrate that a little better. So if the induced voltage drives a current, we know that currents themselves, when they flow in circular paths, form magnetic field lines. So this ring would act like a magnetic dipole, right? And if current were to flow in this counterclockwise direction, then based on the right-hand rule, try it yourself, curl your fingers in the direction of that induced current, and your thumb points upward. So there's a self-imposed amount of flux associated with this ring, right? Well, that's exactly the way the current will flow. The idea is, as the magnet falls, it's pushing more and more flux downward through the ring. So to counteract that, the ring itself becomes a magnet that points upward to compete with the external magnetic field that induced the current in the first place. Hopefully that makes sense. Well, anyway, let's carry on with this demonstration, try to make full sense of it. So the real demonstration is to drop the magnet through a tube, not just a single ring, and then the effect is much more pronounced. Well, a tube is just several rings stacked together, right? I could take a bunch of these rings, stack them all together, and form a complete aluminum tube. So let's state Lenz's law one more time. Lenz's law tells us what the direction of the induced current will be. So the induced current will act as a magnet itself, and its magnetic field is going to do one of two things. One, it's either going to oppose the increasing magnetic flux that produced it, or if it's a case where magnetic flux is decreasing, then the induced current is going to attempt to restore the diminishing amount of flux. So whether flux increases or flux decreases, either one represents change in flux, and Faraday's law says it's that rate of change of magnetic flux that induces some EMF. So if you were just to hold this magnet in place, if this magnet doesn't move, then there's a steady amount of flux, and a steady amount of flux doesn't generate any voltage at all, and so no current flows in the ring and there's no interaction. It's only when the magnet is in motion that a change in flux takes place. So the flux is increasing, 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 increasing. At this instant, the flux has reached its maximum value. As the magnet continues to fall, now that peak value of magnetic flux starts to become less and less and less and less. So while this magnet is approaching, and notice the polarity, the north end of the magnet faces down. So as the magnet approaches the ring, the flux increases, and during that interval, current would flow in this direction in order to oppose the increasing flux. And then as the magnet continues, for an instant, the flux reaches its maximum value, and for a moment the current goes to zero. And then as the magnet continues to fall, now the flux is decreasing. So there will be an induced current to try to restore whatever peak amount of flux had existed for a moment. So the current will reverse direction as the magnet falls away and go back the other way. So think of it like this. For every segment of the aluminum tube, and we've shown one here in red, right now there's not much of a reaction in that red ring. It's basically going to be the top portion of the aluminum tube that interacts with the magnet. But the magnet continues to fall, and it doesn't interact directly with the aluminum because, after all, aluminum and magnets don't stick together. But at about this point, the red ring sees the magnet coming. There's an increase in the downward flux through the ring, and so the ring wants to be a magnet with upward magnetic field to try to oppose the falling magnet that's inducing the current in the first place. So as the magnet first starts to approach, current will flow which way now? Do you understand this? Right. It'll flow in a counterclockwise direction to make some magnetism point upward to oppose the increasing flux downward from the falling magnet. And then the magnet continues on. And as it falls away, see, at this point, there is some amount of flux, and it's as if the ring finally relents and gives up and says, okay, I understand the way this is going. There's some downward flux. And it kind of gets used to the amount of downward flux. And now as the magnet continues to fall, that downward flux that had built up starts to go away, and the ring decides, wait a minute, maybe I want to continue to have that downward amount of flux. And so it wants to put the downward magnetic field back through itself, and so at that point, current would reverse and flow this way in order to restore the downward magnetism that the ring eventually kind of got used to, so to speak. Okay, so I want you to watch the video. I have a demonstration of this very sort of interaction between a tube. I think maybe in my demonstration what I have is a copper tube instead of aluminum, and copper works just as well because it's also a type of material with a very low relative permeability. And I believe on my copper tube I have a cutaway. So you can see the magnet's dropped and it falls, and the speed with which it falls is much less than 9.8 meters per second squared, right? It's slowed down by the interaction between each ring that the magnet interacts with and the magnet itself. So as the magnet approaches, the ring behaves like a magnet pointing up, and so it competes with the falling magnet and pushes it away. Once the magnet has fallen through the ring, the current reverses and flows the other direction, and now the ring behaves like a magnetic dipole pointing downward, and now it attracts the magnet that's fallen below it. So whatever the case is, whether the magnet is approaching and repelled by the ring, or the magnet is receding and attracted by the ring, the force is upward. And this is very much consistent with the law of conservation of energy. Think about it. If it were the other way around, if dropping a magnet through a tube produced a force of interaction between each of these rings and the falling magnet that attracted it while it approached and repelled it as it fell away, then its acceleration would be even greater than free fall. And so we could take a tube and put it on its side, And if this were really the case, we could put a magnet in sideways and give it just the tiniest little flick, just the littlest push to get it moving. And then if the interaction was to attract it as it approaches and repel it as it goes away, the magnet would come out the other side with a much greater velocity than the initial velocity, and that would violate the law of conservation of energy. So in fact, it would work quite the opposite if we put one of these tubes on its side and tried to propel a magnet through it. You give the magnet a good solid flick, and as it approaches this ring, and then the next ring, and the next ring, and so on, each one of these rings is going to provide a force opposite the direction of the magnet's initial velocity and therefore slow it down. So the effect becomes even weaker for the next ring and it slows it down a little more, and ultimately the magnet would come to rest somewhere inside of this tube, consistent with the law of conservation of energy. So if I write Faraday's law one more time, induced voltage is equal to negative the number of loops times the time rate of change of magnetic flux. That negative sign is there to remind us of Lenz's law, and Lenz's law does a couple things. One, it guarantees that the law of conservation of energy is not violated. And two, it makes the induced voltage produce some sort of a self-defeating induced current. Okay, so watch my video demonstrations on Lenz's law.